Okay, for this section we're going to be looking at Earth's processes. That's going to include the plate tectonics, earthquakes, and volcanoes. So we'll start off with the plate tectonics. Plate tectonics is going to be the theory that describes the formation, movements, and interactions of these plates. Some natural processes, such as earthquakes and volcanoes, can cause sudden changes in the Earth's surface. Other processes work more slowly. For example, tectonic plates motion can cause uplifts of the Earth's surface, forming mountain ranges over thousands or even millions of years. It's pretty much our definition of plate tectonics, and without which we really wouldn't have these other things like earthquakes and volcanoes happening, especially with the frequency that they are happening, if the continents didn't move. That's a big reason why we have plate tectonics, or earthquakes and volcanoes, is due to plate tectonics. So we have evidence for these plate tectonics, and again, going back to the labs that we did with this section, we see the similar shapes of the coast of Africa and South America, and it looks like they should fit like puzzle pieces together. But more importantly, we see fossil remains of animals that used to be on the Earth, only living in specific parts of South America and South Africa. And it doesn't make sense if they had to swim across the Atlantic Ocean that they would only be found in these small parts of South America and Africa. So it makes more sense that at one time these continents were closer together, and that animal only inhabited that part of the world. We also see, which is another big feather in the cap for plate tectonics, that we see this same distinctive rocks found in both continents dated back to the same time, which leads us to believe that those rocks formed as one rock layer and then broke apart, and some of it stayed with Africa and some of those rocks stayed with South America. Okay. Played a little animation of Pangea and the breaking apart of Pangea. And you kind of see the way the continents kind of drift and move. And we see kind of North America and Eurasia here, and Africa and South America and Antarctica, Australia, and the Indian Peninsula kind of coming up to complete Asia and kind of fill in the rest of Southeast Asia there. In that animation, helping us get an idea of what's going on with plate tectonics and the way that theory kind of works and fits together. More evidence for plate tectonics is the magmatism that we see in the ocean floors. Some of these rocks record reversals in the directions of Earth's magnetic fields, and we call that the mid-oceanic ridge. Where we talk about the lithosphere, we can substitute in there the crust, and we'll talk a little bit more about other parts and layers of the Earth. But when we're talking lithosphere, we're really meaning or referring to the crust of the Earth. So with this magnetism, when we did a lab where we had magnets underneath a model with ridges for the ocean floor, and we rolled a compass over top of them or slid a compass over top of them, and we've seen the polarity change because of the magnets underneath, and we see that matches up with what's in the Atlantic Ocean where the mid-oceanic ridge is. Okay, and with that mid-oceanic ridge, we see the newest crust forming here in the center. We see then slightly older crusts forming to either side, and notice that they're the same color. They'd also have the same polarity, and their polarity would be opposite of the polarities next to them. So these outside parts here would not only be the same age, but they'd also point with a compass in the same direction. And the new crust is again forming in the middle, and the oldest crust out on the edges. How do these plates move? Okay, when we talk about the inside of the Earth and the mantle and the magma inside the Earth, it comes up in convection currents. These convection currents are going to kind of work for heat transfer in liquids and gases, fluids really. And what it's going to do is it's going to get the warm magma rising. When it hits then the bottom of the crust of the Earth, or the inside of the crust of the Earth, it's then going to drag them, much like a river would, along that crust of the Earth, or that lithospheric area. And that would cause the convection, or the little bit of turning of the crust, kind of again like a river pushing them along, or like a conveyor belt slowly moving these tectonic plates to their current positions. So we look at a little animated graphic here, and we see the heat from inside the Earth rising up, and it kind of bumps into the underside of the tectonic plates or the crust of the Earth, and pushes them in this kind of direction. As it cools, then it warms back up and rises again. And we'll talk more about convection currents with weather, but this is also a great example of how they work with Earth. As we look at the different layers, as the mantle gets close to the crust, on that last slide I talked about the asthenosphere. The asthenosphere is as this mantle kind of cools and hardens and begins to solidify a little bit into the crust of the Earth. It's not quite the crust, it's still molten in lava, but some chunks in there that are cooling and solidifying. It's that transition point from the kind of mantle underneath to the crust above. We look at the types of plate boundaries. We have divergent boundaries, and I list a couple examples of those divergent boundaries there. We have a little animated graphic there showing the mid-oceanic ridge. And we have convergent boundaries, and I give some examples there. We look at the Himalayan mountains and mountain building as a big example of convergent boundaries. When we look at subduction plates, we see subduction plates as areas where we see earthquakes occurring and we see volcanoes forming. We get some deep ocean trenches as well with those type of boundaries. And we look at a little animated graphic there of the Himalayan mountains. With these sliding boundaries and these transform boundaries, we look at plates that kind of don't move up or down in comparison to each other, but they move alongside each other. Much like the San Andreas Fault, when we did a lab where we talked about Los Angeles and San Francisco moving closer to each other, and in 10 million years or so they're going to almost be neighboring cities because of these sliding transformative boundaries. Then we got onto volcanoes, and that's our definition of volcanoes. So we look at a opening in the Earth's crust through which molten rock, gases, and ash erupt and to form landforms that develop around the opening, that kind of distinct mountain feature. Where do volcanoes occur? Their main area is going to be around subduction boundaries, where we're going to have one crust riding over top of another crust, and as that lower crust kind of gets recycled or melted back down inside the Earth, the extra magma that builds up from that kind of will form that volcanic ridge there. When we talk about divergent plates in the mid-oceanic ridge, we could also get volcanic activity there, where we can get hotspots, Iceland. With the hotspots specifically, we did an activity with Hawaii, where we looked at the chain of islands that goes all through the Pacific, the Emperor Chain that kind of comes down more south off of Asia, and then as it starts to move south and east, forming more of the Hawaiian chain and ending kind of close to where the Hawaiian Islands are now, that hot spot, a weak spot in the crust where this volcanic activity has taken place for quite a long time, creating these islands in the middle of the Pacific. Okay, with the types of volcanoes, we're going to look at three types of volcanoes. We're going to look at shield volcanoes, cinder cone volcanoes, and composite volcanoes. And then we watched a little video on the types of volcanoes, and then we moved into earthquakes, and our definition of earthquakes there is just a shaking of the Earth's crust caused by a release of energy. So what causes these earthquakes? It's a result of a volcanic eruption, possibly. Volcanoes can explode very violently. With some volcanic explosions, they will break off part of the mountainous feature around the mouth of the volcano, and that is violent enough to definitely shake the Earth. Meteor impacts, things like the Tunguska or Chelyabinsk, just to name a few examples of meteor impacts. Obviously, the K2 extinction with the dinosaurs 65 million years ago is another one where we could see a large meteor impact definitely creating an earthquake effect on the surface. Strains that build up at fault lines. We spent a lot of time talking about those different divergent, convergent, and sliding boundaries. as potential areas where earthquakes and volcanoes can occur, and that goes back to that theory of plate tectonics. And collapses of caverns, if we're having areas where the voids inside the earth are kind of then falling in or getting filled back up, that can create an earthquake at the surface, or that disturbance of the crust of the earth, the top of the earth. We talked about the somewhat recent earthquake in Alaska, and then we kind of compared that to the tsunami of Japan. And we looked at earthquakes and the type of waves, and we kind of tied it in there with we looked at some of the top earthquakes on the planet. Compression waves, or primary waves, squeeze and stretch the materials as they pass through. So we talk about the crust kind of shrinking or getting compressed and then stretching back out, much like the slinky here in this case, getting stretched or shrunken back down, as opposed to the secondary type of shear waves that cause rock materials to move at right angles, and we see there's these peaks and troughs along that way the wave is moving. We see the tops and bottoms of the wave kind of peaking and cresting as it's moving. Then we started to look at briefly how earthquakes are measured, and we said that seismographs are the way that earthquakes are measured, or at least the tools that are used to measure the earthquakes. And the Richter scale, really not used anymore for measuring earthquakes. What we use now is more of a magnitude scale for measuring earthquakes. And I have a little chart over here that talks about the different magnitude earthquakes and how frequently we expect to see them. So if we're looking at 8.5 to 8.9 earthquakes, we expect to see them once every 3 years. If we look at 8.0 to 8.4 earthquakes, we expect to see them about once a year. 7.5 to 7.9 earthquakes, about 3 a year. You can kind of see the statistics there. And then we looked at this website that shows us some information on earthquakes happening all around the world, kind of live. And we can kind of see some of the maps. These are going to be different than the ones I showed in class because I'm taping this later. But we can kind of see the date and the time here, and we can see some of the different earthquakes that are taking place. And I scrolled through and kind of showed some of the different examples of these earthquakes. When we were looking in class, we seen some higher than 6.0, in that 6.0 to 6.4 area size earthquakes in Japan. But just looking at all these earthquakes, these are all within the last few hours. So earthquakes, what I wanted to show, are constantly happening here on the earth. Even though we don't get many here in Pennsylvania, all of the earthquakes I just scrolled through took place in the last 11 hours on the planet. And here are a couple 6.0 to 6.4 earthquakes happening here in Russia. So we do get those earthquakes quite often. Like I said in that statistic, looking at that chart, we expect like 210 of them a year. So here are 2 of those 210 expected. And again, that's only an estimate. But if you have any other questions on plate tectonics, volcanoes, or earthquakes, feel free to stop by in class.